Okay, I think I'm streaming on YouTube and on Twitch. Okay, so we will be able to start. Yes, everything is here. Okay. So in this stream I will try to make a recap of the project and try to make everything a bit more clear. So this project is CleverHand. Go. This project is called CleverHand, and it is a project that aims to design and manufacture a EMG device, so a device that is able to record muscles activity, and trying to make this device portable, modular, and if possible high density as well. So this is not a new technology at all. There have been a lot of let's say try or devices that have been developed to try to tackle this issue. So one very let's say popular one was the myoband. The myoband was 8 electrodes, 8 bipolar electrodes that were able to be placed on the arm, and that were able to record on real time the EMG activity. So this way, when researchers were trying to conduct some experiment, it was super easy because they just had to slide the bracelet on the arm of the user, and from there they were able to get some information about the EMG signal. However, the issue is that it was recording very slow, and also the main issue is that it has been stopped. There is no more myoband sold, so a lot of research has been kind of constrained and slowed because it was not possible to conduct anymore. Now all the myoband that you can find online, you can find it on eBay or other resellers, but it's either super expensive. So previously the price of the myoband was 200 euro. Now if you find one second hand, you might find it at 600 or more, and you're not even sure that it will be working. So that's why, for example, Meta developed something like this, a bracelet with I think 16 bipolar electrodes. So a bit more electrodes, but the issue is that it has still not been released and probably will be very constrained in terms of how you are able to access all the data, all the recordings. Probably they will make you sign some kind of consent that your data will be shared with them. And you have also the very cheap version that is very nice from SparkFun, I think, that is able to, so it's only one bipolar electrode, so two electrodes that are reading the voltage difference between those 2 points. You can place it on your arm with normal wet electrodes. However, it's not very high density, and one module costs £40, something like this. So it's very nice when you want to do simple study. However, when you want to have something that is quick to wear and that is medium to high density, it will be a bit complex to do it with it. On the other side of the high density spectrum, you have, for example, the OTBO manufacturer that is able to that designed some kind of big acquisition devices. For example, this one, the biggest one, is able to get up to 384 channel at the same time. This one 64 channel at the same time. The issue is that it's not very portable nor wearable. So and also it is quite expensive. Few thousand for each of them. This one is even more, few tens of thousands. So I decided to check how it was possible to design my own EMG acquisition system. So for this, I realized that it was not so complicated. So I put myself some requirements. So I wanted to be wearable. I wanted to have more than 16 channels. I wanted to be able to reach 2000 hertz of sampling rate or more if possible. A minimum resolution of 60 bits. It's quite important if you want to have clean or some precise measurement, and to be able to do bipolar and monopolar. The difference between both is that if we check online with some bipolar, so if you look at how EMG recording is done, let's have some schematic maybe, or maybe we can try with this one. Not very nice. I'm just looking for a nice schematic. Okay, let's take this one for example. Okay, here for example, this one is nice also. So here for example, on this person, the people have probably placed 1, 2, 3, 4, 5 different, maybe more, 5 different pairs of electrodes. And the acquisition system will record and amplify the voltage between those 2 points, and you have one reference for the ground. However, if you want to do monopolar would be you have the reference that is here, and you read the difference between this point and this point, this point and this point. And for example, here instead of 2, you would have instead of 1 channel of bipolar, you would have 2 channels of monopolar. So I want to let the user decide what they want, depending on the experiment, depending on the research. It can be researchers can be should have the choice. And that's one thing also. For example, if you compare to the myoband was only bipolar. Also, I think one thing that is quite let's say in terms of objective, I think the issue with the myoband was let's say the business plan in this in the way that they wanted to sell this product for, let's say, general public, so for everyone, just to, for example, activate the TV with it, or to make any type of teleoperated action. However, it's not really practical, and let's say the software, the acquisition software behind is not yet good enough to be able to decode precisely what the person is intending to do. As a result, they kind of bankrupt, and they were not able to sell as much as they wanted. However, in the research sector, it worked quite well because it's very easy to put, and it's nice to have some simple EMG signal to record. So my project is mainly aiming for research, not for commercial, let's say main public product. I want to keep it very modular, because depending on the research or depending on the experiment you are conducting, you will need a different number of electrodes. So I want to be able to change the number of electrodes that you can wear or that you can assemble for your experiment. I want to keep it quite affordable, and I want it to be fully open source. So from my device, I've already let's say lived different iteration. So I will try to sum up the point at right now. So I want the current modules are able to record 3 to 8 channels each. They can be chained in a bus of 16 modules, so you reach more than 16 channels in total. They are able to sample at more than 2000 Hertz. They have a resolution up to 24 bits. They have the possibility to have the onboard electrodes. That means that you don't need other electrodes. You can directly use the dry electrodes from the board, which saves some money but also some space. And you can do monopolar because all the modules share a common external electrode. You also have some RGB LED in visual feedback, which is quite nice when you are conducting experiments to know which electrodes, which module is which, to know if you are reading some EMG signal, so you can have some visual feedback that would help the experimenter or the user. And the interface, I want to keep it also quite to let different possibilities. So I want to let USB, Ethernet, and Wi-Fi communication possible. With Wi-Fi, you will be able to have something that is really wearable, while with Ethernet and USB, you would make it a bit more simpler and maybe enable faster recording. However, it will not be wireless. So here is let's say a general overview of how it's working. You have one master microcontroller that is communicating through a SPI bus with up to 16 modules. Each module has up to 8 channels. So here it's not this, but if you have 3 to 5 channels with the current module, you can reach up to 128, but you could reach also 8 per module. You have the shared common electrodes for monopolar, and also your ground electrode. Then you will have on the master, you are able to have some micro SD card slots. This way you can record, let's say, directly on the microcontroller and make it a bit faster. You can also stream the data from the Ethernet, Wi-Fi, USB interface. You have also some other features. For example, you have an external sync pins that enable you to, if 16 times 8 channel is not enough, or if you want to place the bracelet or the module at different position on your body, then you are able to have 2 set of modules. So this way you can synchronize them together, or you can also synchronize them with another device. There are different possibilities as well. So the thing is that for now I'm recording EMG with my modules, but I want to let it possible to record other features, such as inertial features with an IMU. So this way each module could read the position or the orientation of each small modules. You could also provide feedback, so electrical feedback or vibrotactile feedback. So I want to let a lot of different possibilities. As I'm aiming for research, I don't need it to be, let's say, super looking super good or caring too much about the design, but I need to let it possible for the researcher or the engineers to extend the possibility. So here are different iterations of the project. I have also here, maybe you can see with the webcam, that it is a bracelet shape of these modules that are connected one to another. So to describe it quickly, the first issue was the addressing system. The requirement was that the module's address should not be hard-coded on each module, because you want to be able to place each module at different place and to use them indifferently. So you need the address of the module to be to depend on the position in the bus. Also, you don't want to use, for example, if you have 32 modules, you don't want to use 32 line to address each of them, to tell them, okay, I'm speaking to you, I'm speaking to you, I'm speaking to you. You could use 32 lines, but then you would have a lot of wires, and it's really not practical. And you want the system of addressing to be fast enough to withstand the 2000 sampling rate. So one first iteration was inspired by this idea of module, where you communicate. For example, if the master sends an information on the 1, it will talk to the first module, and if it sends it to the 2, let's say to the 3, then it will be the first module will translate it to the next one. And so each module just need to read their first pins, while the master is able to communicate on different pins and address them depending on the position on the bus. The issue is here we still have too many pins, too many inputs. So I tried to think of a way to digitalize and kind of multiplex this ID. For this, what I did is an addressing bus of 4 bits that is sending, for example, an address 13 to the first one. 13, the module, if it's 13, the module will be, let's say, addressed only if it receives 15. So when the master sends 13 to the first one, it will not be activated. However, this module will transmit the address received plus 1. So it will send 14 to the next one. So the next one receives 14. 14 is not 15. As a result, it will not be activated. However, it will send 14 plus 1 to the next one. The next one receives 15. Since 15 is activating, it's 111. It will activate the module, and the module will be the one addressed. And this way, the SPI bus, when it's communicating, it will be able to communicate with it. Here a simple diagram. So the issue is that this incrementer is not possible. It doesn't exist in a simple single chip. So I needed to do it with logic gates. To do that, I used this incrementer design. So on each module, you have this pair of 4 gate. So for example, if the master is sending 15, so F, the first module will be activated, while it will not activate the other one. Now if the master sends E, so the first one is not activated, but the next one will be activated, etc. So that's how I did it with 3. So the possibility was to do it with 3 chip, having each 4 gate for the 4 channel for each XOR and AND, and 1 gate NAND for the last one, because the chip select is reversed. So the chip will be activated only when it receives 0, not 1. So you need to reverse the output. So yes, here are the solution. So it is taking some space. The issue is that at the end, you see here on the chip design, this big one is let's say where I'm doing all the amplification for the EMG, and the addressing is taking almost more space than this one. So it's a bit, let's say, frustrating. However, it's not so expensive, so it's nice. Also, the issue is that we are limited to 4-bit, so we are limited to 16 modules. And the propagation time also. So when the master wants to address the last bit, it will send 0, then it will be incremented to 1, it will be incremented to 2, etc. So this propagation will take around 96 nanoseconds. So it is quite fast, and it should be enough. So that's how I did. However, later I discovered this really nice ARM microcontroller that is only 50p, so very affordable, very small, it's taking less space. And I thought also that it's really nice because it has 16 GPIO, so I'm able to have a lot more features on my module. So I would be able to, for example, on each module, activate RGB LED. I should be able to provide more feedback to the user, etc. So I really wanted to use it. However, when I manufacture it and try to program it, I realized that it was not very fast. So I implemented in assembler the incrementing system. However, it's around to do an incrementation, so reading the input port, incrementing them, and then outputting it. It's in assembly, it's around 25 lines of code. So since the ARM microcontroller is turning at 32 megahertz, it's taking around 800 nanoseconds. So the difference is quite huge. In this one, it was 6 nanoseconds. In this one, it's 800 nanoseconds. And you have the same problem of propagation. So just to reach the last one, you need to spend 12 microseconds instead of 96 nanoseconds. So here you have 12,000 nanoseconds. So it's a lot. It's a lot slower than this one, and actually it is too slow for the 2000 sampling rate that I wanted. So since I really wanted to still use this chip to have all the different features, I decided to make a combination of this and another logic gate. This logic gate is an identity comparator. So the identity comparator is quite efficient. So it is quite big compared to the other one. You can see that 9 millimeter, and this one, or even the combination of all the modules were around 20, while this one is 30. So it's taking some space. However, it's the idea I will try to, for example, this one here you can see. So the bus address can just display any value, and each module will compare this value to a value set by the microcontroller at the beginning of the experiment. So the microcontroller will set once the address of each chip at initialization, and this way there is no more propagation because this address is the same on the whole bus, and the chip is able, the comparator is able to switch his output value very fast. Just so that means that when the microcontroller wants to address the last module, it's only take around 14 nanoseconds. So this one has not been yet manufactured, but this is the one I will try to design with you during these streams. Another idea was to stack up those different modules and to make them even more modular. So before I had everything on this one. So on this one I had the electrodes. So the electrodes are on the back of the module. I had the EMG amplification system that is here, plus the crystal, and I had the communication addressing system that is here. However, every time I wanted to change the design of the electrode, if I wanted to, for example, just if I realized that one of my design was not working properly, I had to redesign everything. So with this design, what is quite a bit more efficient is each module is on a separated board that enable quick prototyping, but also it is saving some space because we're using horizontal space by stacking up the different module. So this way you still have the electrodes on the bottom, you have your EMG acquisition system here, and you have your communication addressing system here. And it is very small. So to give you an idea, this width is around 11 millimeters, and the other one is around 15 to 20. So yes, so you would be able to have quite high density with this type of module. So from there, let's go to how is it called? To the design part. So I'm using KiCad. So KiCad is a nice open source system to design electronic board, PCBs. So let's come back, for example, to this one, to the EMG. So in previous stream, I already showed how I place those different components. So it is quite simple. You have your ADS 1293 that has 6 input, and you have your some features for ECG, so for the heart monitoring that we don't care in our case, so we just use standard value for the passive component here. We need some crystal to run the chip quite precisely. The issue is that the crystal needed, the frequency needed for this crystal is existing only in very big package. So for example, if you look at it, most of the board result in having the size almost of the crystal. But in our case, it's not so important because we are able to stack up everything, so we are not really losing the space. Okay, and that's it. And so this one will need to be connected. So this is a communication port that will need to be connected to the communication module. And this one is the one that needs to be put to 0 to activate this board. Okay. One thing I wanted to add was the possibility to have a voltage regulator. So I think I will use the same that Adafruit is using in a lot of board. I think it's AP, yes, 2112. So what is nice with this board, with this chip, is that it's possible to. It is linear, so it means that it is not switching, so it will not add noise to my device, and it will also be able to kind of filter the different noise coming from the power line in the bus. So, and also one very important aspect is that you want to be sure that it is available on your PCB manufacturer. So I always check, for example, on GLC PCB, if this one is there, AP2112. And for example, if you check in stock, so the 3.3, the one that we need, is available, and it's really cheap. It's 10p for one. So okay, let's check if it's already existing in KiCad. So AP1221, maybe not. So the package is, just need to be sure that it is the right package. So this one is SOT 25.5. This one is SOT, but I don't know if it's the right one. So that's the issue with KiCad, is that sometimes the package are not so easy to import or to find. So let's check here. 25, that is this one. So definitely not the same package as in KiCad, because here you can see that there are 6 pins instead of 5. So what we will try to do, we'll try to find it online. So IP 2112. Okay, so here, for example, you can do download symbol and footprint. Yep. KiCad. Yep. I think I already have one. I don't know which one. Okay, good. So download. Don't feel like it's working. Yeah. Okay. KiCad. Okay. 6 hours later. Here you go. So you end up with this that you need to extract here, for example. You go inside. So you have different things. You have this that you care. Let me open another one. Oops. Let me remember. I think it's here in my libs, custom libs. So I will put the step file here. Step. So that it's this one is for the 3D model. Oops. Okay. Then I want the KiCad mode here. Okay. And then, oops. I will need to copy paste this one inside the other one. So let's try. Okay, so if we go in footprint editor, we should be able to find it now. What was the name already? Maybe. That's the one we just added. So it's SOT 95. So this is here, so it has been imported correctly. We just want to add maybe the 3D model. up. We go same space, KiCad, libs, TG, custom, steps, and we said it was SOT. Do we lose it? Let's check again the name. Step. Oh, AP. That's directly the name of the thing. AP. Why cannot I cannot see it? It's clearly here. It's clearly not showing. Do I need to reload it? Oh, I was not able to see it. Okay. Then I need to switch it to turn it a bit because the rotation is not the right one. So rotation, yep, okay, and round up, okay. So here it is with the right direction. So for the footprint it's fine. Now we will try to import the symbol. Takes some time to load. Oops. Okay. So now what we want to do is open import symbol. Oh. Let's select this one to do import symbol. To go where we at this. Up. Ta-da! So now we have our symbol. We can maybe change it a bit because we don't care about all this writing. Up. So much. Taking forever. Okay, finally. Let's check the pinout of the board. So you can see that in this format you have 3 pins here, so V in, GND, and enable, that is here, and you will have this pin that is not connected and just a V out. So if we want to have something similar here, to make it a bit more easy to use, I prefer always, so 3 is enable, it's here, GND is 2, it's here. I prefer to keep the same layout so it's easier after to place the component on the PCB. And here we go. So from there I can just save, close it, and go back in my no, I need to reload it. Yep. Oh, did I set? I think I didn't set. I need to link the right footprint. So up. To be sure that the footprint. Up. And we said SOT. here we go. Save. Too many of them. Okay. And now when I try to import it, I should be able to have it here. And when we go on our board, if we update it, yay, we have it. Okay, so yeah, I want to have it somewhere in the board. I want to let the user have the possibility, or I want to let me have the possibility to use it or not. Okay, here we go. So here you can see that these pins are going to be the pin connected to the electrode board. So if we come back here, we have our board here. So this will be connected this way together. So the electrode board will be connected to this. Since I want to let the possibility to have up to 8 channels, it's important that we have 8 connectors, even if this one has only 6 connection. Okay, then I don't know why this one. Okay, so the pins are not very well positioned. We can see that after. Okay, now we have to check also how to use it. So you see that you need 2 capacitors in input and output. So let's put them here and here. We need a GND. So yes, one thing to keep in mind is that this is a linear voltage regulator, so it is not switching, so it is not adding noise. However, when it's linear, it is dissipating the difference in energy, and as a result, it might hit a bit if the voltage drop is too high. So to tackle this issue, I'm using it on a 3.3 volt input and 3.3 volt output. So this way I have almost no voltage dropout. I'm just using it as a filtering system. I need to connect the ground to this. Okay, and this one as well. Nope. Okay, and we want this to be always enabled. There is no reason to not. Is there? No. That could. One question could be: do we want to enable it only when the chip is enabled? This way, when the chip is not enabled, we don't use power. The issue with this would be that you would need to reset all the parameters inside every time, so not a good idea. Let's check. On is high, so it means that this chip is enabled when the input voltage is high. Let's double check. Vin, you can see that the Vin is between 2.5 and 6, so we should never, even if we input 5 volt from the USB, it should be safe. And then just wanted to be sure that the V enable no, so we will just trust this. Actually, one thing that we can do is check on Adafruit. I think I saw it on the BNO board. if you go in download, if you go in, maybe, no, it will be, no, I don't want this. Let's try this. Oh, it was here. Here. Okay. And so, is that the right one? Is it the same one? No, it's not the same. So maybe it was actually BNO 85. Okay, here probably. Then we go in download. Oh, no. It's here. Okay. Yes. We have it. So you can see that they are directly connected, the enable to the in, so that means that it is enabled when it is high. Okay, just to be sure. And yeah, they wanted 1 micro, I think. So they use 10. Oh, I think it's different. They use 1 and they use 10. I'm not sure which one I should trust. They're doing all the tests on 1 micro, so let's use 1 micro. Up. Same here. Okay. So now we have our power regulation system just here. Which one? How would it look best? Probably like this. Okay. What else? The crystal is already connected. One thing that we can add is some label and global label at the classnet. Okay. So for example, we can call it the in. The v in will be this one actually. Oh, it will be so we have 2 source. I think we will just use the same. Does it matter? Okay, so let's say that we use this for this, and we will use another one. Oops. We will use this, for example, for this one. So it's still 3.3 volt, but filtered, and we will put it here. Up. Here we go. 10 nanofarad. Okay. Anything else? We have all the rest that is connected together. I just added those 2. As we said, we have only 6. One thing I wanted to add was this. I want to be able to connect. What was it already? Oh yeah, I want to be able to connect the shared electrode with the outside here, but with the board I want to let the possibility to cut it. So to cut, or should I do it on the board or on this one? I don't know. Let's do it here for now. So I think it's called I don't remember. Cut. No. Selector maybe. No. I don't remember the name of what I'm looking for. I think SparkFun DigiKey had some oscillator, optical, magnetic, logic, encoder, fuse. Or maybe it's a two-way. Nope. Split. Nope. I don't remember the name. That is annoying. Let's see if I add one in my. Nope. Let's, okay, never mind. Let's just use. I do mind. Where did I use it last time? I think I used it on the previous KiCad. So let's try. Let's ask ChatGPT. I am designing a PCB. I want to make let the possibility to cut a track or solder it back together. together. What is the name component? Oh, jumper. Oh, bridge. Okay. Let's try again. So here we go. Okay, finally. So I want to let the possibility to open it. Which one? This one. Okay, let's do it close like this first. Actually, I don't want this one anymore. Yeah, did it. Again. Nope. It's this one. Okay. And this one do not needs to be connected. 6. Yes. Okay. So let's import the rest. Okay. So, oh, I didn't check. Ah. Not very nice. Jumper. Let's try again. Here, jumper. Okay. Complicated, but I did it. Okay, let's try this. Okay. Here we go. So. Now we will try to connect everything together. So we have different things to connect. So this one here, this one. So we have our two crystals here. Let's make a smaller step here, here, here. Okay, then those two can be put here and here. Okay, then this one is here. We just need to be able to place those two components. For this regulator. So where should we find this place? Show only front. Oops, only front layers. And from there, let's try to move everything back. Will it be enough? So we want some tracks. Let's do 15. So it's maybe a bit too close. Okay, something like this should be a bit better. Then actually this one might be better on the other side. So maybe we want to put it here. So this way we'll have everything on this side. Oops. Here, do we have 5 volt? Don't think we have. Why is it written 5-volt? Tic-tac-took. Oh, here. We don't have 5-volt. We just have this. Okay. Here we go. Okay, not bad. I think it should be good enough for the placement. Maybe we can move it back. Here. This. Should not forget. And in the good. Oh no, not good. We still have those two big pad to put. So would we have the place for maybe one here? What about this one? Oh, maybe the best would be to put them behind. Like this. And we will just move this guy up. We should have just enough space. Close them here. Okay. Then that means we can move that back up. Something like this. We have just an issue with the connector. Okay, and very well. So we just want to exchange. Okay. So this guy should move back up. Should be put. I don't know. Why do I have two ground? Check again. I don't know why. Where should I put this? Okay. However, we want this one to be moved here. Okay. Here we go. Do we need anything else? So it's 15. Do we want to make it smaller? Oh, no, we cannot because of show all layers because of the guy behind. Okay. So here, maybe it's a bit tricky to have it in this order. Okay. Okay. So this board we have six output. So in this case we just want to have just 6 connection to the electrode board. However, in the case we would have 8, we want to keep the possibility to add them here. Okay. Yeah, I think I don't forget anything. Not forgetting anything. I think okay. So what about the position of these? Maybe we want to change them. Do we have names? No, we don't have names. Just to make it easier. So we will have so that put here Mozzi SLK and CSP chip select. Okay, from there we update, have some names, it will be a bit easier. So we want to move this guy. Okay, probably doing something like this. Poof. Everything, and then this one we move it back here. Okay. Should I move this one? Yes, probably. Let's try again. Go. Oh, am I missing one? Okay. Okay. Hopefully I'm not missing anything. Tac, tac, tac. This one. Okay. Maybe. Tac, tac, tuk, tuk. Okay. Okay. I think it's the positioning start to looks like something alright. So let's try to start doing some simple routing, or maybe I should check behind first. So what do we have? We want to move it in the middle. Okay. Here. Okay. Maybe we don't care about this one. Since it's supposed to be something that we want to be able to solder or cut, it's quite important that it is accessible. So let's make it not too much in the middle. Okay. Signature, let's make it smaller. Okay. Here we go. So let's okay. Then okay. Okay. Good. So now we can start routing it. So, yep. I guess having the pad, or if we do it on several layers, should be fine. Yeah. So Then this one should be connected here. Okay, then I think this one is sync and alarm. So we have several pins that we are not using. I'm wondering if we should let them accessible in case. Changing my mind. Maybe something like this. With some space. Okay. Okay. Tic-tac-toc. Am I missing something? I'm just thinking if it's possible to connect them together without via, but maybe it's not really needed. Maybe not. Could do that. Not so great. Okay. It is. So this one we want both to be GND ground plane. So we will add field zone. I don't know why. Yeah, better like this. And we want 5. Yes. And from there, just want to drop this. Oops. So we said on both, and we want GND. I have a GND A. I think it doesn't really matter since we connected both together. Okay. And now we can just here we go. So I think it's fully routed now. Should be fine. I mean, since we just have the EMG acquisition device, it's pretty simple, pretty straightforward compared to the previous boards, but I think it should be fine now. Okay. We might have to come back to it for another iteration, but for now, just let's clean this. I think I have one too many. Tac. I have 2 unused, 3 unused. Okay, that's fine. Just here, okay, and we want to copy paste this. Oops. Okay. So here I'm not doing anything, I'm just making everything a bit more clean. So we did 3.3 volt first. Okay, never mind. Okay, then ground. Then nothing. Then Mizomoti. Okay, it's in the right order. Good. Friends. Up. No. Schematic editor. Yes, I think this is where I am. An online drawing. Symbol. Maybe it's not possible. I thought it was possible to rotate the symbol 45 degrees, but it might not be possible. Cursor, grid thickness, grid option, perhaps. In the PCB there is constraint. Yeah, okay. Not possible. So let's go back. Okay. This one not connected. And let's do the same here. I forgot this one. Okay. Here we go. Okay, maybe we can just come connection. Voltage regulator. Crystal. And finally gate. Okay. Okay. So it will be EMG DAQ module. Good. Okay, I think we have our first module here. Good. So from there, we want to open, let's say, communication. Okay. We have this is our board. So this is a communication board with HC32L110 ARM microcontroller, and this is the identity comparator. So this is the addressing system plus 2 LED to give the feedback. So let's see. So we need to do the schematic routing. Let's like this. Okay. So we need the same thing as this one. And look, double check which one is this one. Is it in the right order? That's the question. So we have G3. Oh, it's not at all in the right order. Okay. So something like this. And here we update and we change the order. So we want to use this. Okay. So first 3.3 volt. But we want to move here. Then ground. Then nothing. Then miso. Mozi. Miso, Mozi, and finally okay. Now we are back in the right direction. 3. Okay. Okay. Put this on the side. We have our 2 LED. Good. We have our ARM microcontroller. Good. So this will go with the microcontroller. So let's call it address module. Address bus. Okay, and then from there Okay. It seems that on Twitch it has stopped from a long time. Oh, no, maybe not. Okay. Okay. Background. No, G. Something else. What is it? What is G? It's one. Oh, so this is the enable. No. It has to be put low so that it works. Okay. This is the output, so this will be our chip select. This is 3.3 volt, I think, I hope. Yep. .3 volt, everything's alright. Okay, then we will have to decide which pins do what. So for that we'll use 32. Nope. My internet is a bit slow, I think. This one, I guess. internet is super slow. Okay. Very helpful. Let's nope, here. Normally I already set what all of them are able to do. So okay, my internet is getting too slow, so I think I will stop the stream here. But yeah, let's start again later to finish this board and try to see what we can do. Okay, see you, bye bye.